Starting from today, we will work on the Module 4, Divide and Conquer approach. Yeah. So this module is very important. The two most important modules in this class, Module 3 and Module 4. Yeah. All right, so let's do Part A today, Insertion Sort. Yeah. This is our third sorting algorithm. Yeah. The first one, selection sort. Second one, the bubble sort. The third one, insertion sort. After that, we have a few more sorts we need to learn. Yeah. Like merge sort, quick sort, and heap sort. Yeah. All right, 8.1, insertion operation. Yeah. Let's look at the question first. The same old question, problem number 4. Yeah. So you're familiar with the problem already. Yeah. So let's do the analysis. Yeah. First, regarding the strategy. Yeah. To solve this problem this time, this is our third time to solve this problem. Yeah. So we want to find a completely new algorithm. Yeah. We should forget about the first and the second. Yeah. Our two old algorithms, we should completely forget them. Yeah. And we also need to change our view of this question. Yeah. So we want to look at this problem in a completely new angle. Yeah. All right. So from the strategy, we still apply one of our old strategies we used many times. Yeah. So start with a simple case. Yeah. Yeah. And then after that, we grow the data size, or we call the problem size gradually. Yeah. So every time we increase the problem size by 1, yeah, we just add one more element to the previously solved problem. Yeah. All right. Then we need to consider how to connect two adjacent cases. Yeah. Regarding this question, we have some experience from Module 3. Yeah. In the recursive algorithm. So remember at that time when we try to find the recurrence relation, we need to consider two adjacent subproblems, right? Subproblems. Yeah. At that time, we mentioned this divide and conquer approach. Yeah. We talk about that. Yeah. And we need to, divide the given problem into two smaller subproblems, right? Yeah. After that, then we need to consider, the gap between two subproblems. Yeah. One larger size, one smaller size, and what's the gap between them? Yeah. Here we have the same situation. Yeah. We need to find a way to connect two adjacent cases. Yeah. And there is a gap between two adjacent cases. So we need to, find a way to handle that gap part. Yeah. All right. Yeah. Let's work on the problem size. Yeah. When we start, so we want to start with the simplest case. Yeah. So what's the simplest case? Yeah. An array containing only one element. Okay. Yeah. That's the simplest case to start with. Yeah. But if we treat this special data case as an array, it is automatically ordered, right? Yeah, we do not need to do anything. Yeah. There is no need to do any comparison here. Yeah. It's already ordered. Yeah. After that, then we consider adding a new element into this ordered array, A1 element. Yeah. And we can easily see if we only need to do one comparison, yeah, no matter A1 greater than A0 or A1 less than A0, after one comparison, we can get our data ordered. Yeah. Okay? Yeah. So after comparison, yeah, we assume our array is ordered. Yeah. Then add another new element, A2. A2, now we need to, using the minimum number of comparisons, yeah, to get all the elements ordered. Okay? Yeah. Yeah. So here, yeah, you have best case, worst case. Yeah. The best case, A2 greater than A1, you only need one comparison. You can get the whole array ordered. Yeah. But most of the time, we want to look at the worst case. Yeah. All right. So the worst case, you need to do two comparisons. You need to compare A2 with A1 first. After that, because we need to imagine we may have the worst case. Yeah. So if A2 less than A1, you need to do the second comparison. Compare A2 with A0. Yeah. Yeah. But in any situation, two comparisons must be enough. Yeah. So you can get a whole array ordered. Yeah. Then we keep doing things like this. So we can consider a general case. So this is the general case. We assume these k elements have already been ordered. Okay? Yeah. Then we want to add a new element, AK. Yeah. And best case, worst case, yeah. So you can get the idea, yeah, how to get them ordered, right? Yeah. Yeah. But here, when we do the analysis at this point, so you can see, something interesting. So you want to summarize a little bit at this point. Yeah. So we add a new element to the currently sorted array and make it sorted. Yeah. So this whole thing we are doing, so you can, try to understand, yeah, the essence of this whole thing. Yeah. So we make our observation. What we are doing is basically insert an element in a sorted array at the right position. Yeah. So the position could be anywhere in this array, right? Yeah. Yeah. Any position is possible for the new element to be inserted. Yeah. Here, yeah. The keyword is this insert. Yeah. So what we are doing is an insertion operation. So we need to study this insertion operation. Yeah. All right, next. Yeah. Let's study the insertion operation. Yeah. Let us use some, diagram to help us understand the details of this insertion operation. Yeah. Shift elements for insertion. Yeah. So we need to, really figure out all the details when we implement this insertion operation. Yeah. All right. Yeah, so why we say shifting elements to the right, we need to do this type of operations. Yeah. Let's look at the diagram. Yeah. For a typical diagram like this, yeah. Now we need to understand the details. How do we insert this new element at the right position in this array? Yeah. Okay? Yeah. First, we need to find the right position for this new element, right? Yeah. At the beginning, we don't know. Yeah. So after a few certain number of comparisons, eventually we will find the right position for this element. Yeah. But after that, yeah, we need to, in order to place this new element at its right position, we need to find an empty location for it, right? Yeah. Yeah. That location must be empty. Okay? Yeah. Otherwise, if that location is occupied, you cannot put there, right? You cannot replace the old element by this new one. Then you remove the old element, right? Yeah, you don't want to do that. Yeah. So for that consideration, you need to do the shift operation. Yeah. So you don't want to throw away your old elements. Okay. So when you do shift operations, you still keep your old elements. Yeah. All right. So let's implement that idea. Yeah. When we start, yeah, because here we can assume the new element eventually will be located somewhere. Yeah, here let's use this arrow to represent its right position in the array. Yeah. But when we find this place and provide a vacant location for this new element, we need to do some work, right? Yeah. So let's do step by step, to get it ready for the new element. Yeah. All right. So when we start, let's lift. Yeah, because originally the element is here, right? Yeah. At the beginning, the element should be here. Okay. All right. So, but we want to move the element in this location, to its destination location. Yeah. So to do that, we lift it. Yeah. We store it in a temporary location. So this is a temporary location. Okay. All right. Then, after that lifting step, this location is empty, right? Yeah. Now we can, do the shifting operation. Yeah. But we need to compare the value with the first element. Yeah. If AK minus 1 is greater than AK, then we can do the shift operation. Shift to its right next right element. Yeah. Yeah. So one position to the right. Yeah. All right. Yeah. After the shift, this location is empty. Yeah. Then we compare AK with the next element, AK minus 2. If AK minus 2 is still greater than AK, then we do another shift operation, one position to its right, and so on. Okay. Then eventually, yeah. So here we assume this is the last element. We need to do the shift operation. Okay. After that, last shift operation. Yeah, so we have this situation. Yeah. You can see, yeah, this location is empty. Yeah, all right. Yeah, vacant. Yeah, but we still need to do another comparison. Yeah, because still you do not know if you still need to do another shift operation, right? Yeah. So you have to another operation, and that's the stopping step, the last step. Yeah. So you need to have that stopping step. Yeah. So the last step, the comparison result should be AI less than or equal to AK. Okay? Yeah. Yeah. When you hit this condition, then your insertion step should be completed right here. Yeah. So you drop the AK element to this vacant location. Yeah. So you complete the insertion. Yeah. So that's the whole process for the insertion operation. Okay? Yeah? Yeah. All right. So then, now you can see, yeah, when you do this one typical insertion step, yeah, you need to do many comparisons and many shift operation. And then what is the shift operation? Yeah, yeah. Visually, what do we see visually? Yeah, so that's the shift operation. Yeah, but underlying operation, that's the assignment. Okay, you assign one element to a different location, from its current location to a different location. It is basically an assignment operation. Yeah. Here, so we can count the number of assignment operation in this step. Yeah. If we use asymptotic notation, so that is big theta of k. Yeah. K, that means the number of elements here. Okay, number of elements. Yeah. Big theta of k. Yeah. So for the big theta of k, because you have best case, you have worst case, right? Yeah. Best case, yeah. Best case is 1. The worst case is k, right? Yeah. But the average case, and that's 1/2 times k. 1/2 times k, yeah. So if you asymptotic notation to represent this average case, 1/2 of k. Yeah. All right. So next, yeah, we need to look at the whole insertion sort, the implementation. Yeah. So we're almost there. Yeah. Yeah. Because, we just apply the standard insertion operation again and again, and at the end we will get the whole array sorted. Yeah. All right. Yeah. But let's do the efficiency analysis. Let us estimate the number of comparisons we need. Yeah. Here, although we have two types of operations, assignment operation and the insertion operation, but we treat assignment operation and a comparison operation, but we treat comparison as the basic operation. Yeah. Yeah. Although every time we need to do one comparison and one shift operation, yeah. Yeah, but let us just count the number of comparisons here. Yeah. All right. So that's the diagram for a typical insertion operation here. Yeah. Let us count the number of comparisons for the worst case. Yeah. So for the worst case, we need to compare AK element with all the other elements, right? So one element for one comparison. But that is for one insertion. Here, to sort the whole array, we need to consider all the possible insertions. Yeah. The first insertion operation, you do one comparison, right? Yeah. The second, you do 2, and so on. The last one, you do n minus 1 comparisons. Yeah. Here, the n here is the total number of elements in the array. Okay, all right. So you get this formula, 1/2 times n minus 1. Okay. If we use the asymptotic notation, we can write big theta of n squared. So that is the worst case. Yeah. Next, we want to consider the best case. Yeah. So for the best case, every insertion step, we only need to do one comparison. From beginning to end, all the way, each insertion step, it is one comparison. Okay, all right. So then, because we need to do n minus 1 insertions, so the total number comparison n minus 1. Yeah. If you use the asymptotic notation to represent it, it is big theta of n. Here you can see the difference between the best case and the worst case. It is very big. Yeah. N versus n squared. That difference is very big. Yeah. Okay. All right. So you can see how different comparing with best case and worst case. The difference is extremely big. Yeah. Because here when we say big, later we will compare the difference between best case, worst case for all other sorting algorithms. This one is the biggest. The difference is the biggest. Yeah. So you will see. Yeah. All right. And this property, actually the big difference, this property is very important for insertion sort. So this property could be useful, in some real world situation. Yeah. So later we will take a look how to use this property. Yeah. All right. After that, we need to consider the average case. Yeah. To consider the average case, we can do like this. Yeah. Average case, so we can consider what is the average case for each insertion step, right? So remember in the previous slide, we say 1/2 times k. Yeah. But this k from 1 to from n minus 1, right? Yeah. Yeah. So then you take average. Yeah. So here you can see, because for the worst case, you have the dominant term is 1/2 n squared, right? Yeah. That's the dominant term. So we throw away the minor term. Yeah. But for average case, if we use this formula, you can see the dominant term is 1/4 of n squared. Okay? So then it is still big theta of n squared, right? Yeah. But you need to use 1/4 as the leading coefficient. Comparing with the worst case, you use 1/2 as the leading coefficient. Yeah. All right. Yeah. All right. So that's the efficiency analysis. Yeah. All right. So then we complete this insertion sort. Yeah. Yeah. So you can see, pretty simple, right? Yeah. All right. Yeah. But at the end, we need to make our final conclusion, based on the main property of this insertion sort. Yeah. So what's that main property? Yeah. All right. If the given array is almost sorted, that is our data property. Our data has this property. Okay. Yeah. So the data here, have this property. Okay, so this is our data. All right. Then, the insertion sort is a good choice for sorting. Yeah, let me use a simple diagram to explain the special property for the data. Yeah. Let me draw this line segment representing the whole array. Yeah. But this array is almost solid. Yeah. So not solid, yeah. Almost solid. Yeah. Not solid. Yeah. So we use these scattered red circles to represent the parts of the elements that are not ordered. Okay? Yeah. Other than these red circles, all the other places the elements are ordered, except these, small places, not ordered. Yeah. If your data has this property, then the best algorithm to get the whole array sorted, that is this insertion sort. Yeah. Why? Yeah. The reason is very simple. Yeah. Very simple. Why? Because although it's almost sorted, not quite ordered, but if you sort it by the insertion sort, is it very close to the best case? Right? Close to the best case, right? Yeah. Yeah, because if the whole array is ordered, then that's the best case, right? If the whole array is ordered, then you apply insertion sort on this array, you get the best case. But here, not 100% ordered, but only very small portion of the data not ordered, then it should be very close to the best case. And for the best case, we have big theta of n, right? Yeah, big theta of n. So that means it's very close to this big theta of n. Yeah. So the performance is very close to this best case performance. Yeah. All right. But if you do not use insertion sort, so later, as I mentioned at the beginning, we will learn 3 more sorts after this one. And if you apply any one of the remaining 3 sorts, the best you can get is big theta of n log n. N log n, you have extra log n, you need to multiply that n. So it is worse than this n, right? So you can see, that's the main property of the insertion sort. Yeah. All right. But under the special situation. Yeah. So if in real world applications, when you encounter data with this special property, then don't forget to try insertion sort to solve your problem. Okay? All right, so that we complete this insertion sort topic. Next, 8.3 example. Yeah. Sort 4 elements array and sort 5 element array. Yeah. There are 2 questions, 2 problems, 2 sorting questions. The first one, the second one. All right. Because the ideas we are going to use to solve these 2 problems closely related to the insertion sort. Yeah. So for then, because we just learned insertion sort. Yeah. So our understanding is still very fresh. So let's apply the main idea. Yeah. Definitely we need to modify slightly. Okay? Yeah. Then, as a practice, let us use that idea to solve these 2 problems. Yeah. The first one is not very hard, but the second one is pretty hard. Yeah. this one is pretty hard. Okay? Yeah. Yeah. Because later, yeah. Today you will learn the solution. Yeah. So after that, if you want to challenge your friends, you can ask them to sort 5-element array. Yeah. So usually, for a very smart person, that person still needs to use several hours to solve this problem. So that's the typical situation. Yeah. All right, let us look at the solution one by one. Yeah. All right. Yeah. Let me use this blank slide to explain the first solution. Yeah. All right. The question first. Yeah. Yeah. Our simple statement for the question. Yeah. So that's here. The goal is we need to sort a 4-element array. Okay, all right. For simplicity, we assume the elements are distinct. Okay, yeah. Yeah. But later for the general case, yeah, we can easily modify for the general case. Yeah. All right. And we can represent our array, the 4 elements array, x1, x2, x3, and x4. Okay, so 2 elements. Okay, so our goal here is, yeah, that's goal. Yeah, but so let me write the question statement. The question statement. Okay. Find the minimum number of comparisons to sort this 4-element array for the worst. Now, you can see we always target the worst case. Yeah. All right. Here, yeah. Also, we need to consider the worst case. All right. Yeah. All right. Let's consider the solution here. Okay. Yeah. For the solution here, because we just learned insertion sort. Okay. Yeah. Yeah. So it's very likely people want to connect this question to the insertion sort. Yeah. All right. But before we, get the solution details. Yeah. So from the direction view, yeah, understanding the direction, its direction. Yeah. Yeah. We should not be restricted to the insertion sort. Yeah. Because the insertion sort may not be the best solution. Okay? Insertion sort is a solution that sort array. But here, our goal is we want to get, so that this minimum number tells us we want to get the best solution. Our goal is to find the best solution. Okay? Yeah. That's the main difference. Okay? Yeah. Yeah. All right. Yeah. But the idea used for the insertion sort, we can still borrow that idea, right? Yeah. Yeah. But you need to prepare, at the critical step, you need to prepare to make some change in the insertion sort. Okay? Yeah. Ready for the change. Yeah. 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 All right. Yeah. So when we start, we can use the insertion sort idea to get started. Yeah. All right. When we start, we have this one element array. Now we want to insert next element into this ordered array. We know by one comparison we can complete that insertion step. Okay? Right. So after that one comparison, we can get this small array ordered, right? Yeah. The next step, we need to insert x3 at some appropriate location. Yeah. For the worst case, we know we need two comparisons. Worst case, two comparisons. Okay? So after the two comparisons, we can get these three elements ordered. Yeah. Here we assume like this. Okay? All right. Then the last step, we want to insert the last element into this ordered array. Then, because so far at this point, we just repeat that insertion sort, right? So this is already the last step. Okay? If we still follow the standard insertion step, then we just repeat the insertion sort. Okay? So we may not get the best solution, right? So here, in order to get the best solution, at this step, we should try our best using the minimum number of comparisons to get this x4 element join the ordered array and to get the whole data set ordered. Okay? Yeah. Here we also know, if we, by the insertion sort, this last step, okay, by the standard insertion operation, okay, how many comparisons we need, okay, to get a x4 inserted into the currently 3-element ordered array. We need 3 comparisons, right, for the worst case. Because 3 comparisons for the worst case. But the questions, can we do better than this 3-element comparisons? So we want to get, x4 element inserted into this ordered array. Can we do better than 3 comparisons? If you can do better, then you make improvement here. Okay? All right. You can do better because the first element you want to compare is compare x4 with x2 first. Okay? After that, you have 2 cases, right? If x4 greater than x2, then your next comparison with x3. If the x4 is less than x2, your next comparison with x1. you only need two comparisons to find the right position for x4, right? Yeah. Yeah. So this step, you do not need to follow the standard insertion step. Yeah. So you can compare with the median element. That's different from the insertion step, right? Yeah. So comparison. Okay. So here you can see when you compare the median, it is very similar to the binary search, right? Yeah. So you know the binary search. Yeah. Yeah. Actually, our next topic will be binary search. The topic of part B will be the binary search. Yeah. It's another very important basic algorithm. Yeah. So we need to learn the details. Yeah. Yeah. But here, yeah, you know, based on your background knowledge, you know a little bit about binary search, right? So we always compare the search key. Here we treat this X4 as the search key. We always compare the search key with the median of the current array. Yeah. Median of the current array at each step. That's the binary search way. Here, if you use this binary search idea, you can reduce the number of comparison from 3 to this 2. That's improvement. Okay? That's the improvement. Yeah. All right. Now you can get a better solution. Yeah. Because, yeah. So here we can continue, you know, from this way. Yeah. By the insertion sort, we need 6 comparisons to sort a 4-element array. We know for the worst case, right? Yeah. All right. But here, the total for this algorithm, the total is 1 plus 2 plus 2 equals 5 comparison. Okay? Yeah. So better than the insertion sort. Okay? Yeah. All right. Then the question. Yeah. Can you do even better than this one, this 5 comparison solution? In other words, can you use 4 comparisons to sort any given 4-element array for the worst case? Yeah, yeah. So if not the worst case, then it doesn't count. Yeah, you have to solve it for the worst case. Then it counts. Okay? Yeah. That's another question, right? Yeah. Yeah. Try to use 4 comparisons to solve this problem. Yeah. All right. So here, let me give you the answer here. Yeah. The answer is no. A big no. Okay? You cannot do it. Nobody can do it. Nobody in the world can do it. Okay? Yeah. That means this algorithm, this one, 5 comparison solution, this one is optimal. This algorithm is optimal. Okay? The question, how do you see it? It's optimal, right? How do you prove it? Yeah. You need to prove it. Okay? Yeah. You need to rigorously prove it, right? Yeah. Yeah. Yes, we can do it. Yeah. We can do it. We can rigorously prove it. Okay? Yeah. But not today. Today we do not have that much time. Okay, we have another, after this one, we have another sorting 5-element array, another question we need to solve. Okay, yeah. So I will leave that topic, okay, yeah, at the end of this module, module 4. At the end, I will talk about that topic, yeah, how to prove it. Yeah, yeah. So that is a very important result. Yeah. But the background, so you need a lot of background to do the preparation. Then you can understand. Yeah. At that time, I will give you a formula. The formula, based on that formula, you can calculate the number of comparisons you need to sort, so that formula is, we call the lower bound formula. Okay, lower bound formula. So that means nobody can use fewer number of comparisons than that lower bound number. Yeah. Here, based on that formula, we calculate this 5 is the lower bound. Okay, the 5 already hits the lower bound. That means nobody can break that lower bound. Yeah. So we have a rigorous proof. Yeah. That formula gives us a lower bound. Okay? Yeah. Based on that formula, this is the lower bound. So then, this algorithm is optimal. Okay? All right. Yeah. Yeah. Let's move to our next question. Yeah. So this one, we need to sort 5-element array. Yeah. So the goal, sort a 5-element array, and we still assume distinct element. Okay, yeah. And with these 5 elements. Right? Yeah. All right. Yeah. This one is very challenging. Yeah. 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 All right. Without using the background knowledge from this topic, insertion sort, yeah, so it will be very hard, yeah, because here we have a lot of preparation, mainly our insertion sort background, yeah, so we can do much better. Okay, yeah, so we can solve it, not too hard, yeah, not too hard, yeah, but finding this solution is not easy. Yeah. Here I can say, with the remaining 10-something minutes, yeah, a little more than 10 minutes, yeah, so we can complete its solution, yeah, including the analysis part. Yeah. All right. Yeah. Before we start, yeah, so we just solved a 4-element problem. Yeah. 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 So you can connect, many people may want to connect to our previous solution, right? Yeah? How much different? What's the difference? So this 5-element question and the previous 4-element question, what's the difference? Because we already know the solution of that 4-element question. We just add one more element, then we can get a 5-element solution, right? Yeah, you can try that first, because that is an easy method, easy solution. right? Yeah. We may not be able to guarantee that easy solution is the best one, but let us try it first. Yeah. Okay. Yeah. So this is our first try. In our first try, when we start, we apply our previous solution first. Yeah. That previous solution tells us we can sort the first 4 elements. We can sort it with 5 comparison, right? 5 comparisons. Okay, all right, yeah. All right, after that, yeah, so the next step, because we need to do insertion, right? Yeah, yeah. Insert element 5 into the currently ordered array with 4 elements. What is the minimum number of comparisons do you need? Yeah. Yeah. So here we know we should not use the standard insertion operation, because based on our experience in the previous question, we know we can do better than the standard operation. Yeah. So you can, the success of the previous solution, we know, based on the binary search, right? Yeah. So here, the binary search, you can compare with X2 or X3. Yeah, similar. Yeah, because you have even number of elements. Yeah. If you compare X5 with the first comparison, then you need to consider the worst case, right? Yeah. The worst case is X5 greater than X2, so you need 2 more comparisons to find the right location for X5. You don't want to assume, that's the case. That won't be the worst case. So the worst case, for the worst case, you need 3 more comparisons for the worst case. Yeah. Then total, this solution, the total 5 plus 3, you get 8 comparisons. Yeah, this one, you get 8 comparisons. Okay. All right. But the question, do you know if this solution is the best or not, right? Yeah. Because our goal, we want to find the best solution. Yeah. The solution may not be the best, right? Yeah, it may not be the best. Yeah. Remember, I mentioned in the previous slide, I mentioned the formula, lower bound formula, right? I mentioned that. Yeah. Yeah. Here, I do not give you that lower bound formula. Yeah. 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 I want to show you at this point. Based on that lower bound formula, the lower bound for this 5 element array is 7, not 8. Okay? Not 8, it's 7. Lower bound. Okay? So that means we have a little room for the improvement. Yeah. Yeah. People may argue that lower bound may not be achieved, right? Yeah, it's possible. Yeah. Although it's a lower bound number, but it may not be guaranteed that lower bound can always be achieved. Yeah, that's true. Yeah. We just hope we want to achieve that lower bound. Yeah. But it's not 100% sure. Yeah. It's not 100% sure. Okay? Yeah. We don't know. Yeah. But here, at least, there is a possibility to improve the current solution, right? Yeah. All right, so let me try it. Okay. Let me use the remaining approximately, let's say, 10 minutes to find a better solution. All right, so let's try a new idea, okay? Yeah. All right. So for this new idea, we use our experience. Yeah. At this point, yeah, in this class, so far at this point, we should have a lot of experience, right? Yeah. So we have learned, a lot of algorithms, ideas, problem-solving strategies. Yeah. So we should be able to do a lot of things. Yeah. All right. The first round we want to do, the first round, yeah, let me write this. Yeah. Tournament method. Yeah. We're familiar with this tournament method, right? Yeah. So this first round, let's apply the tournament method on this 5-element array. Yeah. All right. X1, X2, we compare these two elements. X3, X4, we do comparison. Yeah. So we assume X1 is the winner, X3 is the winner. Okay? All right. After that, compare X1 and X3. We can assume X1 is the winner. Okay? All right. Here you can see in this tournament round, we need a comparison 1, comparison 2, comparison 3. 3 comparisons. Okay? Yeah. So after these 3 comparisons, next we need to, do some cleanup work. Okay? Cleanup work. Yeah. To see what we have so far. Okay? We want to view the current state of our data. Yeah. All right, so we use a diagram to represent the information we collect so far after the first round, tournament round. Yeah. All right, so you can see what we have is X1 largest, yeah, so I write the highest dot. Next, X3 lower because it is smaller than X1. Yeah. Then X4 lower. Yeah. For X2, we know it is smaller than X1, so we draw like this. Yeah. But we have a last element X5, we don't know, the relationship of X5 comparing with the remaining 4 elements. All right. Yeah. Here we set our target. So 7 comparison. That's our target. Yeah. So we want to get that. Okay. Our goal is that. That means we need 4 more comparisons. Yeah. We cannot waste any of our comparisons. Just 4 more. We should get it. Okay. All right. Yeah. Then, next question. How do you want to do your comparison number 4? Okay? Yeah, because that is very important. That's critical. Comparison number 4. Yeah. Here, you need to find an efficient way to your comparison number 4. Yeah. Yeah. All right. Yeah. Yeah, because we do not have a lot of time, so I want to, get to the point fast. Yeah. All right. Here, when you observe your data, you need to catch that main property here. The main property, so look at these 3 elements. These 3 elements, we know they are ordered, right? Yeah. So these 3 elements, they form an ordered subarray, right? Yeah. Here, I would like to call it, in our data, in our current data, these 3 elements form the longest ordered chain. The longest, this is our longest ordered chain. Okay? So when we do our comparison number 4, we want to compare this element, new element x5, with our longest ordered chain, and we try to insert x5 into our longest ordered chain. Insertion. Do the insertion. But when we do insertion, we do the binary search type insertion. So that, we know, when we do the binary search, we compare x5 with the median. Median is x3. Okay, that's the comparison number 4. Okay, when you do comparison number 4, you have 2 cases, right? The first case, x5 greater than x3. Yeah, so here, if I write case 1, that is x5, let's say greater than x3. Yeah. Case 2, x5 less than x3. Okay? Yeah. 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 But for each of the 2 cases, you need another comparison. So number 5, or another comparison here, number 5. Yeah. To get x5 inserted into the longest ordered chain, right? Yeah. So here you can see this is our second round. This second round, in this second round, we need 2 more comparisons. To get x5 inserted. Okay? Yeah. So the first round here, this is our second round. Okay? Second round, insert, we can say the goal of the second round, insert x5 into the longest ordered chain. Okay? Yeah, so the result, 2 more comparison, we can get it. All right. Next, our round number 3, the last step. Yeah, step number 3. Okay? The last step, so we need to, summarize what do we have so far. Yeah. Cleanup work. Yeah. Do some cleanup work. Okay? Before we apply our last 2 comparisons. We have only 2 comparisons left. So for the last 2 comparisons, so we really need to do things carefully. Yeah. All right. So after round 2, what do we have? We only have 2 situations we need to consider. Yeah. All right. Because after round number 2, our longest chain becomes 4-element array, right? Yeah, because we get x5 inserted into the previous longest ordered chain. So the 2 cases, like first x5 is at the top, then x1, x3, and x4. Yeah. So x2 is here. Yeah. Yeah. That's the first case. The second case, x1 is at the top. Okay? But after x1, then the following 3 elements could be in different orders, right? Yeah, yeah. But there are several cases. For several cases, we only need to pick 1 representative, yeah, because they're equivalent. When the structure-wise, they are equivalent. Okay? Yeah. So we do not need to look at all the 3 possible cases. Yeah. So here we can assume one of the 3 cases like this. Okay? Yeah. Yeah. All right. Then x2 is here. Okay. All right. That's the starting point of our round 3 comparisons. Yeah. All right. After that, then now we need to join, insert, you can call insert x2 into the current longest ordered chain, but there is, this edge. Yeah, this edge is useful, right? This edge, for this case, you only need to compare x2 with x3 and x4, okay? 2 more comparisons is enough to insert x2 into the current longest ordered chain, right? So number 6, the space too small. All right, so you know it, here. Number 6, okay? Number 7, all right? But for this case, all the 3 elements we need to compare x2 with, but we can apply the binary search way, right? Yeah. The binary search way, number 6 comparison, if greater than x5, 1 more, number 7, right? If less than, 7th comparison should be here. Yeah. So in either case, you just need, so here, round number 3, you need 2 more comparisons to get x2 inserted. So you're done. Yeah. So the final total, you need 3 first round, 2 second round, another 2 third round, you get a 7 comparison. And based on, I previously mentioned lower bound formula, this is the optimal solution. Okay. So because you touch the lower bound, right? So this solution is optimal. Yeah. That's it. So we complete this one. Okay. All right. So let me stop right here. So we finish part A of module 4.